All right, thank you very much for the kind introduction and for inviting me here to give a talk. I have to say that a disclaimer that I just slept 3 hours last night. So I might say something wrong, but there's a good excuse. Okay. So, all right. The title of the paper is the statistical limit of arbitrage. It's going to work with my other student, Doug Garland, Rina, and Numerical is my colleague. Dai is joining on Ian and Kelly next, starting from this year. All right, so there's a lot of equations in this paper, but if there's only one you want to take home, there's only one that is important, which is the first one, that the pricing errors are not equivalent to arbitrage opportunities. Okay, so pricing errors here means, alphas, for example. Okay, but alphas does not necessarily translate into arbitrage opportunities. This is kind of a key equation or inequality that we will discuss today. All right, the real motivation of the paper is about limits to arbitrage. Okay, so if you think about Roth's arbitrage tracking theory, all right, so the theory roots out near arbitrage opportunities based on the true parameters in the return generating process. Okay, so given that stock returns follow a Beck's model, okay, and Ross and his authors later on establish an equivalent condition showing, alphas need to be very small, otherwise it's going to be an arbitrage. But in their prediction, we assume that arbitrageurs know which stocks have alpha and precisely how large the alpha is. As a result, arbitrageurs can build a standard mean-variance portfolio, and based on that, they derive their this statistical theory. Now, this assumption that arbitrageurs know true parameters is fairly common in economics, right? So this is the rational expectations assumption dating back to at least Lucas, and who made it famous, who made a very popular assumption in macroeconomics. Now, in practice, however, arbitrageurs do not know which stocks have alpha. They have to learn that from the data, right? So, that's the reason why Hackathon hires so many of our students, because they're good at doing statistics, not because they are, from the finance group or whatever, not because they know a lot of finance. All right. So, if you think about the difference between, rational expectations and doing statistical inference, sometimes the rational expectations assumption is benign. Because the idea is, as long as the sample size is large enough, eventually the parameters will be reviewed from the data. And so that's why rational expectation assumptions are approximately okay with as long as you have a large enough sample. Now, in the case of arbitrage pricing theory, this is not that easy, because in the original EPT of Ross, he has to assume that the number of assets grows to infinity. All right, so that there is a trade-off between the dimension of the assets and the time period. All right, so if the dimension is really high, then it is impossible to learn alphas very precisely. Right, so this is the kind of the trade-off we're exploiting in today's time. Okay, so at the end of the day, the challenge of learning a large number of parameters will induce a limit to arbitrage. Okay, so and truly due to statistical learning. Now, this is certainly a new mechanism, a new channel, an alternative channel relative to the existing literature on limits of arbitrage, which is actually summarized in this annual review of financial economics paper. They kind of document, they actually survey literature, and they kind of argue the arbitrage limits might be induced from noise creating risk, short run cost, financing frictions, etc. Okay, so we kind of come up with a new theory, truly based on statistics. All right, let me explain the key message of the paper using just one feature here. Okay, I'll make sure everyone understands the story we're going to tell. Okay, so I guess many of you have heard the story that economists working down the street saw $100 and now pick it up because someone else would have picked up if it was a real dollar, right? So arbitrageurs are not that lucky. They're not looking at hundreds of dollars. They're looking at $1 bills on the ground. There are many of them. Okay, and unfortunately, most of these $1 bills are fake. All right, so if you pick them up, you get zero utility. And some of them being negative. Okay, so if you actually pick it up, you lose $1. All right, so this is the word that arbitrageurs, in particular statistical arbitrageurs, are facing. Okay, now because there's so many of these $1 bills, it is impossible for arbitrageurs to find all of the authentic dollars. They're not able to find all of these dollars, given limited time or given limited sample points. As a result, there must be some real dollar bill left on the graph. Okay, this is the story we're telling. We're gonna kind of explain this using rigorous statistics. All right. So the paper is kind of part of the conference topic, which is machine learning as a pricing. But much of this literature focuses on factor portfolios, the stochastic discount factors. This paper is different. Okay, we're going to focus on the alpha component of cross-section of returns, not the factor part. Okay, we're going to be able to tell you how much the factor-focused approach will miss, how much opportunity, how much investment per opportunity the factor-based approach will miss. Now, the paper is clearly related to the learning literature. All right, there's a large literature in asset practice. We're not the first one to argue rational expectations is problematic. Okay, so there's already kind of a long list of learning kind of papers. But all of these papers are learning about cash flow parameters, which is typically a small dimensional parameter. As a result, with the sample size goes to infinity, there is no learning effect in the limit, because the parameters are asymptotically revealed. We're going to propose a new learning scenario where even in the limits, there is going to be learning difficulty because the large n relative to t. As a result, the learning effects in our scenario will not disappear, okay, even asymptotically. I think this is something new to the literature, okay? All right, let me first summarize the theoretical results, okay? So, as I have indicated, in this paper, we document a statistical limit to arbitrage. An arbitrage purely due to statistical learning. And we do that in a linear asset pricing model. The exact model Ross developed is okay, so that's the model. And we are the only kind of difference is that we require arbitrageurs to learn from the historical data. So arbitrageurs cannot use real parameters to do their robotics. They have to actually use feasible trading strategies, because feasible if the strategy use historical data. Okay? And in this economy, we show there is a statistical limit arbitrage. Now we also derive the optimal feasible Sharpe ratio achieved by any strategy. Okay, so apparently this optimal strategy is different from the usual invariance analysis strategy, which relies on knowing parameter numbers. We further show that there is a gap between this feasible Sharpe ratio that we developed and infeasible Sharpe ratio that is optimal in Ross APT, where you know all the two parameters. So the interpretation of this gap is entirely, the gap is entirely due to learning. Now, I like to think of this feasible Sharpe ratio as a good measure of investment opportunities in the data. All right, because you can actually achieve it. And I like you to think about the infeasible Sharpe ratio in Ross studying as a measure of pricing errors, like how much pricing errors there is in the data. That kind of goes back to the first inequality that I discussed in my talk. Pricing errors are not equivalent to arbitrage opportunities. And we demonstrate that how this optimal feasible Sharpe ratio varies with the strength and sparsity of alphas. Now you can imagine that if alphas are very strong, very large, there's a lot of them, it's very easy to learn them from the data. Then there is no difference between rational excitation limit and feasible limit. So in this case, there is no gap. Okay, so the optimal feasible strategy naturally converts to the Sharpe ratio that is exactly the same as the Sharpe ratio of the optimal infeasible Sharpe ratio. Okay, now, but if alphas are rare, okay, and very small, the learning is hard. Okay, and in this case, the gap is large. Okay, so and I'm going to show you that in practice, we're more like in a scenario where there is a sizable gap between the two chart ratios. All right. So in order to rigorously show that there is nothing else arbitrators can do to close the gap, we actually have to design an all-weather feasible trading strategy. By all-weather, I meant even without knowing the conditions of R, okay, regardless of being large or small, I don't need to know it. I can design this trading strategy such that it is optimal in all scenarios. Okay, so then arbitrators can just apply our strategy to achieve the optimal chart ratio. Okay, so in the beginning, we give you an upper bound of the chart ratio, and then we design trading strategy to achieve it. So that kind of closes any kind of gap in the theory. And finally, we examine all sorts of machine learning strategies that exploit, multiple testing, shrinkage, and selection techniques. Right? These are very popular among practitioners. We'd like to know whether these strategies are optimal, under what conditions they are. Okay, so we do some analysis for that as well. Now let me summarize our empirical findings. Okay, so empirically, all right, we effectively, our empirical results are effectively conditioning on a factor model, right? That kind of starts the whole thing. Okay, so we use one factor model, which 1727 factor model, which is very, very close to the MSCI R model that industry is using. Now, the reason is we like to deal with individual stocks, not portfolios. And to deal with individual stocks, you really need a model that can capture time varying data. Okay, and industry people are very smart. They're not estimating time varying data. They assume time varying data are known, which are stock characteristics. Okay, so we kind of follow that kind of strategy. So our model assumed like 16 kind of style, if I was word, 16 style characteristics and 11 industry examples. And for this factor model, we regress next month's return cross-sectionally onto this month's characteristics, and that cross-sectional R-square on average over time is about 8%. And it turns out, that means that there's a huge amount of idiosyncratic risk that cannot be explained by beta exposure. Which means that alphas are very hard to learn. Okay, alphas are very hard to learn. So we also actually calculated. So there's about 6% of stocks that alpha greater than with t greater than 0, and 0.6% with t greater than 3.0. So alphas are not very strong, and they're relatively speaking rare. Okay, so that's one more thing. And finally, we use feasible arbitrage portfolios. And we realized that the best strategy gives us a Sharpe ratio that is as low as 0.5. This does not take into account transaction costs. If you take into account transaction costs, that Sharpe ratio is going to be even lower. So the conclusion is ABT is possibly right, at least for this model. Okay, so you can think of what we're doing is an empirical or economic test of ABT, not a statistical test of ABT. Okay, so I'm going to be more clear about it in a few minutes. All right. So in the interest of time, I'm going to quickly go over the literature. We don't have enough time for it. So clearly, this paper is related to the arbitrary pricing theory. So this is an update of the classical theory. And there's a literature on rational implementations in asset pricing. And Lars Hansen has written a lot of papers on this topic. And we are kind of closely related to these ideas and limit arbitrage as well. Now, I'd like to spend more time on this literature, right? This literature that many of you are very familiar with. So the empirical asset pricing literature around 20 years ago, Professor Zhou and a few others started to work on this problem. What is the optimal portfolio allocation when parameters are unknown? Okay, when parameters are unknown. Clearly, it's not invariant stuff because parameters are unknown. Okay, so that's why a lot of people are starting to think about plugging sample mean, plugging sample covariance matrix, and studying the properties of that estimator. And not surprisingly, that estimator is not optimal. It's only good under very restrictive assumptions when n is much smaller than t. Okay, so what we are doing here, it turns out that even though we have very different motivation, we happen to find a solution to this problem. Because we also kind of have to find what is optimal strategy when arbitrators don't know the model parameters. That's exactly the problem they're trying to solve. Okay, so under the facts of model assumption, we actually provide a solution to this problem. All right, so there's also a lot of related to return visibility and portfolio formation, so that's the upside. So the point that I want to make here is that most of this empirical asset pricing literature, like in machine learning strategies, you have to choose a lot between factors, right? So I can ask so many times, like how do you choose that, how do you choose that, whether it's optimal or not. Clearly, it's not possible to be the best between parameters. It is not possible we're using the best architecture. Someone else will be very smart and come up with a better architecture, with a better tuning parameter, get a higher trap ratio. From that point of view, all the empirical trap ratios and portfolio performance are just lower bounds, right? At least you can achieve this much. There is not much discussion about upper bound. To study upper bound, like how much machine learning can do, you really need a theory. Okay, so that's what we kind of propose. All right. Finally, the paper is closely related to literature on testing APT, as you can imagine. Now it turns out most of the econometricians, me included, when we're testing APT, as soon as we find a rejection, right, typically use some sort of chi-square test or TRF test. By the rejection, you walk away. All right, so rejection, you walk away. Okay, your test has power. But that's not what economists should care about, right? So if you just find rejection because there is one single alpha that is very large, that's not economically important, even though we might have statistical significance, right? So that's why we need to look at how much rejection statistically translates into economic, performance of sharp ratio portfolios. Okay, so that's kind of what we do here in this. All right, so in terms of statistics, what kind of strategies we're using? We're also bringing something new to the asset pricing picture. So we're looking at rare and big signals in statistics. So this turns out to be like a very important line of work within statistics and very difficult line of work, starting from John Tukey. And we can borrow lots of insight from that literature. Now, the paper turns out the optimal strategy that I'm going to show you relies on non-parametric empirical base, okay, which is also something very cool from the establishment that we actually follow up. All right, so let me now show you kind of a toy model first to make sure everyone gets an idea, of the limits of arbitrage, statistical arbitrage. Okay, but this is a toy model. Okay, so it's certainly not meant to be realistic. Okay, so let's assume there is an n-dimensional return vector RT with an n-dimensional parameter alpha. Okay, and plus UT, which is idiosyncratic error. UT is completely ID cross-sectionally and over time. And so in this model, there's no factor, right? So just Q alpha returns. All right, with knowledge of alpha, so if you know how large alpha is, the optimal portfolio is just sigma minus 2 times alpha. Okay, so sigma is a scalar. All right, so sigma to the minus 2 alpha is the optimal portfolio. So as you can see, the portfolio weight just depends on the relative large size of alpha, right? So if the stock has larger alpha, naturally it has a higher weight. For this trading strategy, the Sharpe ratio, which is the optimal one, is given by S star square root of sigma minus alpha transpose alpha. This is the optimal Sharpe ratio achievable. Ross has actually used that as well in ECPT. All right. Now, let's suppose that arbitragers cannot use the 2 alpha to build their portfolio. It's not feasible. They have to learn it from historical data. Now, a very straightforward thing to do is to pick sample average, right? So that's very natural. So alpha hat is a sample average of returns that is centered around alpha with a noise U bar. Okay, so in other words, arbitragers do not have precise signals, right? They have kind of noisy signals. Let's for now assume sigma is known. Okay, this turns out not important because sigma is much easier to learn than alpha. Sigma is like, in this case, sigma is one single parameter. Very easy to learn than alpha. Okay? So that's why it does not make a difference at all asymptotically when you assume sigma is known versus sigma is not known. All right, so this is kind of the strategy. Okay, sigma minus 2 alpha hat, which is the optimal one, which is one strategy that mimics the optimal strategy. That alpha, you use that, right? So out of a sample, you can do some very trivial calculations. Let me skip these slides. You just have to trust me that out of sample Sharpe ratio look like that. Okay? So clearly, if T is very large, and it is very large relative to N, which is the sample size, which is number of the dimensional the cross-sectional dimension size, then this ratio is going to be very close to sigma minus alpha transpose alpha. Right? So that means if you have large enough sample relative to the cross-sectional dimension, and under other very good conditions, there is no gap between the feasible Sharpe ratio out of a feasible strategy and the optimal Sharpe ratio possible. Okay, so there's no gap. In reality, we know N or T can be anything. Okay, so it can be anywhere from 0 to infinity. Now, as a result, the ratio between the two, the Sharpe ratios, is going to look like that. Okay, so this term can go to infinity, for example. All right, so there could be a very large gap between the feasible and the infeasible Sharpe ratios. All right, this story looks like fairly simple. However, there's a lot of loopholes, right? So first of all, why arbitragers have to use this strategy, right? So why do you have to use this strategy? Use this alpha hat. Maybe there's other alpha hats that can list for a higher Sharpe ratio. Okay, so therefore we need to look for the optimal strategy. Okay, optimal strategy in the setting where we don't know random outputs. All right, so this is just a figure. Okay, so now let's move on to a more realistic model that is exactly the same model Ross uses for his APT. I think it's a first order approximation. Okay, it's not a great model, but it's a first order approximation. So here we have returns. Now we have beta. Okay, VT plus gamma is the vector portfolio. Gamma is the restricting and VT is the vector innovation. Okay, so together it's like Kagan, for example. Okay, so alpha are the present errors. Now again, for the sake of presentation, I'm going to make sigma u the idiosyncratic error identity. So I not only know they're the same, I also know they're equal to 1. Again, this is not important. In the paper, we don't need that. All right. A more important assumption, though, is that we're going to assume beta is observed. Because empirically, when you apply Barra model, beta is assumed known. Vector is unknown. You run cross-sectional regressions to estimate vectors. Okay, so we kind of want to match that literature. So we assume beta is known to you. Okay, you can choose whatever characteristics you like for beta. All right. Another good reason when beta is known is that you can construct this anomaly like regression, really simple linear regression. Okay, so if you multiply this n beta on both sides of RT and the right hand side, you get that. Under good enough conditions, n beta RT becomes exactly the model of the toy model that we discussed. Right, so this is actually the standard approach to find residuals in cross-sectional regressions, right? So in other words, if I can find optimal strategy for the residuals, like W, then I can easily multiply that W by n beta to get a good optimal arbitrage portfolio with weights in terms of, or written in terms of raw returns. Okay, because that's what we do in practice. All right, so this one I have to tell you that we can just focus on the toy model. Okay, of course, econometric theory, we have a ton of theory to explain why this does not matter. Okay, all right. So now let me quickly review the classical arbitrage pricing theory by Ross. Okay, so I'm going to write it in a way that is more conformal with our notation. Okay, so a strategy W is set to generate an arbitrage at time t under a sequence of DGTs. So here, this is a terminology that we're going to look at large n as n goes to infinity. T has nothing to do here. Okay, so the conditional variance for fixed t. Okay. As n goes to infinity, n is the dimension, right? As n goes to infinity, if you have a strategy with conditional variance close to 0, conditional mean bounded below that constant, then you have a conditional infinite Sharpe ratio, right? So that's arbitrage, okay, according to Ross. And then interval, by the way, the Sharpe ratio, okay, based on this is going to be square root of alpha transpose alpha. Okay, sigma is identity, remember? So it's gone. All right, so interest will show that the condition of absence of near arbitrage is equivalent to that this thing is bounded by a constant. All right, so it turns out that APT never says alpha should be 0. Okay, even though we combinations used to test like alpha equal to 0, so sharp now, right? What APT tells you is alpha cannot be too large. That's all you can say from APT. All right, so in other words, APT allows trading strategies or investors that learn some alpha subject to the idiosyncratic risk. The only restriction APT imposed is that this operation cannot be infinite. Okay, just to be clear. All right. So now, we have seen kind of the notation of classical APT. Now I'm going to give you a slightly non-trivial example to tell you that the classical APT is inadequate. Okay, to kind of model reality. All right, so this is just an example. Okay, we don't need these assumptions. So in this example, we assume alphas are drawn from this distribution cross-sectionally. Okay, so it has the probability rho over 2 with a constant mu, and probability rho over 2 minus mu, 1 over rho, probability 0. This should remind you of the $1 picture that you have seen earlier in my talk, right? So mu is $1, and minus mu is actually $1, etc. So the reason I like this distribution for alpha is that it's super insightful in the sense that mu and rho exactly captures the strength of alpha and the sparsity of alpha, right? So I can actually study how the sparsity and strength of alpha affects the optimal Sharpe ratio we're going to talk about. All right. Now, suppose investors can only make inference about alpha using constant T period of return. And let's make this particular example more interesting. Okay, so let's assume that mu is about this large, 1 over 30. Okay, so in other words, as the sample becomes larger and larger, the statistical problem does not become trivial. They become completely trivial. So mu is about this large, and rho is about this large. Okay, again, these are just examples. All right, so in this economy, if we use an infeasible strategy, W equals to alpha, then the infeasible Sharpe ratio goes to infinity if square root of n over 3 goes to infinity. Okay, so in other words, Ross will tell you that in this economy, there is infinite Sharpe ratio for arbitrageurs. There is arbitrage in this economy, infinite. Now, if you calculate the strategy that I showed you a few slides earlier, there is no arbitrage. Okay, because the feasible Sharpe ratio goes to 0. So there is an infinite gap between infeasible and feasible Sharpe ratio. Now, what I haven't told you is that even if you're using the optimal training strategy, that Sharpe ratio will also go to 0. Okay, so intuitively, the reason is signal is too small, right? 1 over 30. So if you think about the sample average, the error is also 1 over 30. So basically, arbitrageurs are impossible to tell true signals from the cross-section of assets. Okay, and there's not many alpha either. As a result, they cannot get Sharpe ratio out of this time. All right, so now we get into the most important part of the paper, okay, the theory. How do we solve this problem? Okay, first of all, we would like to study the impact of feasibility constraint. All right, so all we add to Ross economy is a feasibility constraint. What would happen? Okay, so if we have this constraint. So let's assume we have an arbitrary factor neutral strategy. Okay, factor neutral strategy means this strategy is orthogonal to beta. Okay, so this strategy will not learn any risk premium. This strategy will just purely learn alpha. Okay. SW hat is the Sharpe ratio generated by this strategy. Now, the feasible strategy means it's a function of observables from t minus t plus 1 to t. Okay, so starting at small t, we look at capital T period, and you can build a trading strategy based on the data. There, okay? So the first theorem says as long as W hat is feasible, as long as it's feasible, okay, nothing else. Then the Sharpe ratio of this strategy is going to be bounded by this quantity, SG squared. Okay, so in other words, we find an upper bound of the optimal feasible trading strategy strike ratio, which is given by that. Now, what determines this optimal feasible strike ratio? Turns out it's not alpha transpose alpha that matters. It's the conditional, it's your best prediction of alpha given all the information that has realized up to T. That actually, your best forecast actually affects your optimal strike ratio that you can achieve based on this arbitrage strategy. Okay, so this is actually a key result. All right, I'm going to now with this result, of course, we can actually generalize or revise interval result that this would be the no arbitrage condition. But wait a second, right? So we still want to understand this quantity, right? So far there's no statistics. Okay, we want to understand this quantity a little bit better. Moreover, we're going to design a trading strategy that achieves this strike ratio. Okay, so now this upper bound is actually sharp. Okay, this strike ratio bound is sharp. Okay, all right. So now let me get back to the slides that we devoted to Professor Zhou. Okay, so he's sleepy, but it's really well. So this is his kind of the exact slide for him. Okay, so for any feasible strategy that we have, this time I don't require vector. Okay, for any feasible strategy that we have, the optimal strike ratio is determined by the strike ratio that you can learn from the alpha plus the SPF strike ratio. Okay, so this is the optimal strike ratio you can ever get in the case of parameter uncertainty. Now the estimation of these quantities are trivial relative to the estimation of these quantities. That's why you don't have expectation or conditional expectations there. The gamma is a small dimensional parameter, and the sigma v is a small dimensional covariance matrix. Okay, so this parameter is much bigger than. And this is actually the sharp upper bound that for any trading strategy in our economy can achieve. All right. So now it's time to actually give you some numerical numbers to understand this optimal strike ratio. So I'm going to call it SOPT for simplicity. Okay, SOPT squared. All right. First of all, I'm going to simulate this DGP. Oops. You can simulate this DGP for a number of rows, a number of mu. Okay, to show you how large the ratio is. Okay, between SOPT and S bar. Now, the x-axis from the right to the left, you're kind of looking at mu increases from 0 to about 10.95 strike ratio in strike ratio scale, annualized. This is, of course, unrealistic, right? No individual stocks can learn a strike ratio 10.11, right? But this is the number that we put here, just to illustrate, give you a very wide range of DGPs. Now, the y-axis goes from 0.12 to 50. So this says like 50% of stocks. So you're here, 50% of the stocks are up. Okay, so if you're here, pretty much barely any stocks are up. All right. So this table basically considers lots of DGPs. All right, lots of DGPs. So now if you look at it, the ratio is almost equal to 1 near this end. When the ratio is equal to 1, it means rational expectation approximation is good. Because the feasible strike ratio is the same as the feasible strike ratio. Okay? But look at this, right? So in order to achieve rational expectation, in order for us to expect this to be a good approximation, you really need very strong signals. Okay? But if you are around this area, there is a sizable gap between passing errors and maximum opportunities, purely due to statistical learning. All right. To better illustrate which area is more realistic, let me just show you a numerical number of SOPT. Okay, in the same XY table. In reality, most of the time we hear people talking about strike ratio between 2 to 4, like very good strike ratio around 2 to 4. So in reality, we're probably around here. We never hear any kind of learn strike ratio 70. Okay, so this is actually an area where that's highly unrealistic. But it is also the same area where rational expectation is served as a good approximation. Okay, so as a result, we know rational expectation is actually a terrible assumption for this economy. Okay, so we're actually more likely here. All right. How much time do I have?
Here's 3 o'clock.
Great, okay. All right, very good. So now let's talk about constructing statistics. Okay, let's talk about constructing optimal strategy. Okay, so again, the first step is to actually get residuals. Because in this paper, we care about statistical arbitrage. Factors are neutralized. Okay. All right. Now, if we know the prior density of alpha, okay, if we know prior density of alpha, we can actually derive the Bayesian optimal posterior distribution of alpha. So that's actually going to be the optimal forecasting. But we don't know that, so I have to estimate it. The practice of estimating prior is essentially empirical based. Okay, so that's the connection with empirical based. We're not making any assumptions that alpha follows Gaussian or anything. Okay, alpha distribution is reasonably, behaved, but nothing else. We make no assumptions on that. So it turns out we don't have to estimate the prior, so we can actually use Tweedy's formula. So Tweedy's formula says that the conditional mean of alpha I, given the sample mean of alpha I hat, is actually given by this formula. Why we care about this expectation? Because under good conditions, alpha I hat is the summary statistics of this information set. So that's why we can reduce this quantity, which is what we care about, to this quantity. And then we apply Tweedy's formula, and this is actually the optimal trading strategy. Now we have to estimate it, right? So this strategy is an unknown function of alpha I hat, the sample average. So from here, you already see the intuition. Okay, so you should not use alpha I hat to plug in as your best alpha to form portfolios. You should do some Bayesian thing. Okay, so if alpha I hat is really large, you don't need to do any shrinkage. You can just use it. But if alpha I is very small, you need lots of shrinkage to actually help you make this portfolio strategy work. All right. In the interest of time, I have no time to discuss, how do we actually estimate it. This PA is actually the marginal density of alpha I hat. So this is something that you can easily estimate non-parametrically. And you have to take derivatives, and then you will be able to construct a trading strategy. Okay, so this is supposed to be have the optimal trading strategy, which is an estimator of that. I use alpha I hat to denote it. Okay, so all right. Now the key result of the paper is that suppose this is the Sharpe ratio based on that strategy, and then we can show that under all DCPs, okay, under all possible DCPs, this strategy achieves the optimal feasible Sharpe ratio. All right, so in other words, we designed the feasible strategy that achieved upper bound that we studied. Now there is some tiny detail because we allow a large number of DCPs. So SOPT could be infinity. Okay, so when SOPT is much larger than 1, the first term matters, the second term does not. So we're looking at percentage differences. When SOPT is small or is equal to 1, we're looking at absolute differences. Okay, so this is in this end we have optionality. All right, so now let's talk about alternative strategies. Okay, so the first strategy is cross-sectional regression, alpha hat, the one that we started. Okay, the toy model, the one we use in toy model. This is actually the most popular strategy among practitioners. They run a cross-sectional regression, find some estimate of alpha and directly use it for portfolio. Or some people suggest we should do both discovery control. Okay, you should find out the threshold tau such that you only trade large enough alphas, ignoring all those that are smaller than tau because you want to control both discoveries. Some may suggest using lasso. Okay, so but in any case, turns out none of these strategies are optimal, not surprisingly. Okay, so but let me give you some intuition why they are not optimal. First of all, we look at the ratio between cross-sectional regression strategy and optimal feasible Sharpe ratio. It turns out when signals are very, very tiny, this strategy, cross-sectional regression, is actually optimal. That's intuitive, right? Because you don't want to do anything else. Any statistics methodology, if all signals are very tiny, you might just want to pick the simplest one. Okay, so without doing anything, just using cross-sectional regression alpha is actually optimal. Now, in which scenario this strategy is not optimal? This is the area. Okay? In this area, there are some alpha that are really large. And they are not a lot. Okay? So that's why you want to do something to pick up those significant alphas, right? And assign a higher weight to it. And don't trade those large number of small signals. Okay, so that would be an optimal strategy, right? But cross-sectional regression is not. So that's why there is a gap. Let's look at the pH, okay? So the forced error rate control approach. So when signal is very small, okay, this strategy is optimal. All right, because forced error rate is tiny, right? Signal is very strong, very easy to learn, and forced error rate control does not do much, right? But if signals are very weak, you do not want to use forced error rate control. That is too conservative, right? You worry about forced error rate control, and you lose a lot of training opportunities. Okay, so in other words, right, false discovery rate control is a statistical objective. What we care about here is optimal sharp ratio, which is an investment of objective. All right, so you should actually allocate some weights to small signals, small p statistics. Okay, so they may contain some signals in it. You just have to be careful about it to actually trade on it. Okay, so let me see the last one. All right. So to conclude this paper, I still need one more piece, which is to estimate at star. So it turns out even though we cannot construct a trading strategy to realize the optimal sharp ratio in feasible one, but we can still estimate it, like how large it is. Okay, so it turns out the estimator for the infeasible sharp ratio is the exact sum of squares kind of thing that statisticians use to test the alpha. Okay, so when statisticians do the chi-square test to test the alpha, they're actually testing the optimal infeasible sharp ratio. All right, so you can actually build a statistics to actually test it, to estimate it, and we can actually convert it. So let me kind of give you some intuition why you can do this. So think about you have lots of coins instead of $1 bills. Okay, so some coins are fake, some coins are real. Even though it's impossible for me to pick up all the real coins, but I can just simply weight all the coins to figure out how many fake are there, how many real coins. Right, so that's why we can measure how much big coins are there, right? How many big coins are there, but we cannot pick them up. Right, so that's why what I'm saying is infeasible sharp ratio is a measure of how much pricing error there is in the economy. Feasible sharp ratio is how much you can actually trade out of it. Okay. All right, so now let me move on to the empirical analysis. About 5 minutes. All right, so as I have indicated, we're going to look at a cross-sectional regression setup there, where we have these 27 factors. Okay, so we have 16 characteristics, 11 fixed dummies. This model essentially mimics the MSCI bar models. We empirically replicate that model. And this is actually a good choice of characteristics as well. As you can see from here, these are characteristics that people use, right? So, academic finance are also proposed. Okay, so instead of picking whatever characteristic we like to use, we kind of make sure that we follow bar. So this is like a constraint, okay, to make sure we don't do great things secure. So we stick to the bar. Okay, so now let me first of all show you the cross-sectional R square over time. So in earlier days, cross-sectional R square is high, like 20%. Okay, these days cross-sectional R square is only like 10%. So there's a lot of noise in the data. And very hard to learn out because idiosyncratic error, the part that R square cannot capture, is exactly the uncertainty of learning about R. Okay. So, and then you can actually look at individual statistics to test individual alphas or individual stocks over their life cycle. Regardless of how you kind of truncate or use moving window or whatever, or use the entire window, the T statistics and the sharp ratios all look like this. So there's a very few strong statistics. Okay, and very few stocks have large sharp ratio. So we are indeed in a scenario where individual stocks are very tiny and rare alphas. All right, so now this is a slide for the feasible trading strategies. Okay, so we implemented optimal one, the cross-sectional regression one, the BH, and the last one. Okay, so one thing you can see is that all these trading strategies give you a Sharpe ratio of about 0.5. All right, so you're not able to achieve very high Sharpe ratio. That indicates using this strategy through arbitrage, ADT is pretty good. There's no much arbitrage. And as you can see, toward the end of the sample, everything becomes essentially flat. That is because monthly trading is too slow for this period, right? Hedge funds now have all updated the strategy to be much faster. This just happens to be the period where 2 Sigma, Citadel, and random Fintech technology are developing into a huge hedge fund. Right, so they were working a very good time to do this, to arbitrage. All right, so even though these strategies achieve similar Sharpe ratios, some of them are terrible. Okay, so BH on average say like 2.4 great stocks, so it's too conservative. It happens to have a good Sharpe ratio, but it's not a portfolio. Okay, and the last one is very volatile. Sometimes choose 700 stocks, sometimes choose no stocks, so it's not very stable because the tuning rank selection is very high. Our strategy and the cross-sectional regression those kind of have about similar number of stocks we trade. So this also tells us that cross-sectional regression is not too bad as a strategy. That maybe agents in the economy are using that and they are actually quite optimal because in reality alphas are very big. Okay, so we're in a region where cross-sectional regression is actually optimal. So this is a slide to estimate the invisible Sharpe ratio, which is the blue line. The orange line is the biased one. This is actually the non-biased one. So you can see on average it's about 3.0. Okay, so there is a huge gap between invisible and visible Sharpe ratio. So if you're a statistician, you will be able to tell, oh, I reject alpha equal to 0, and you walk away. Okay, but we would like to know like how much non-significance we can get. All right, let me conclude. Okay, so in this paper we show stat limits of arbitrage. Important, even though we don't have a equilibrium model, but the important equilibrium interpretation is, mispricing can actually survive. Okay, in the presence of arbitrageurs, and this bound is much wider now than before. And the existing empirical evidence provides a lower bound, we do upper bound. Now, more importantly, okay, so the message we want to make is the gap between physical and invisible, which is the key result of the paper, stays on the wider. Because rational expectation agents, they know everything. All right, so if alpha is time varying, they know alpha is time varying, and they will trade accordingly. Statisticians will have a hard time because alpha, learn time varying alpha is almost impossible, right, with a short window. So that's why the gap will become larger if there are additional statistical difficulties. Okay, so that's why the key message of the paper is delivered with the same model that was developed with OTT, even though I know there are much better models these days. Thank you very much.
Okay, now we open the Q&A session, so we can take questions from the floor.
To change the model so that alpha is drifted over some way. I mean, you have sort of model where you're learning some other alpha. Can you do that?
Right. So I could not derive it theoretically. As long as you make alpha time varying, I'd have to completely change the strategy. Right. So it's hard to derive it. Now, but my argument is, alpha is time varying, the gap between rational expectation and it's going to be wider. So the key message stays there. Right. So let me kind of also comment on the fact that many hedge fund managers are modeling alpha with additional characteristics. Just like we modeling beta as a function of characteristics, they model alpha also as a function of characteristics. And this is actually quite easy to deal with because many of you are familiar with the IPCA strategy, right? So if alphas and betas are linear functions of characteristics, you can actually regress return onto characteristics, right? In other words, form characteristic portfolios, and that portfolio will follow a constant parameter, vector model. So that's why our theory still applies. Okay, so just to be clear, so I know some of you are, share the same question about relation models. So you can totally do that. Okay, so in fact, in the relation of the paper, we do look at portfolios as left-hand variables instead of stocks. Okay, so you get very similar results. There's a huge gap.
Do we have further questions?
Okay, I just asked a related question. Because here you try to use Bala model to motivate, the beta. And so here beta actually characteristics. And the underlying assumption is that beta is right.
Yes.
And then alpha is constant. Right?
Oh, yes.
Yes. So this is just a kind of inconsistency I see.
Absolutely. So you make a very good point, right? So empirically, we're respect the fact that beta is not error. The reason is all the theory that we have developed. If you put a small t for beta, nothing will change. Okay, this beta is observed, nothing will change. But if you put a small t under alpha, okay, so you make the statistician suffer much more because you have to additionally consider smoothing across time to estimate alpha hat at each point, and that makes the whole theoretical analysis less elegant, right? So that's why we use this kind of inconsistency. Because I guess when you do theory, you're supposed to use a stylized model, right? Now empirically, we apply it to time beta and also moving windows estimate alpha, okay, to address this issue. But to fully address this problem, the best approach is IPTA, right? So if you first project down to arithmetic, then the model exactly becomes the same as we discussed. With a tiny difference that when we use IPCA, the factors and betas are all latent, right? So here is known. So there is a tiny theoretical gap there. But right. So but other than that, everything is.
So when you talk about optimal Sharpe ratio, are you just examining Sharpe ratios of arbitrage-based strategies?
Right.
Because optimal Sharpe ratios usually involve both alphas and betas, right? But
Well, what the last sentence was?
the optimal Sharpe ratio usually involves both alphas as well as beta, right?
Right, exactly. So this paper is about statistical limit to arbitrage. So maybe a better title is statistical limit to statistical arbitrage. Because in raw CPT, the agents were using statistical arbitrage, right? So statistical arbitrage validated that perfectly hedge the betas. Okay. So we do have the results, like I quickly talk about it, which is here. So this result actually gives you the optimal upper bound for any strategy, including factor exposure. And all of the changes in this actual Sharpe ratio, which is the optimal FPI Sharpe ratio, right? So it turns out this is the optimal you can achieve. If you don't want to do factor neutral, right? So we do have this result.
I have a very naive question. So you mentioned that the estimator for the optimal Sharpe ratio has a bias. So I was wondering how much that is driven by the Bayesian assumption that we have, the prior around zero.
Oh, so for the optimal infeasible Sharpe ratio, there is a bias because large and large t thing. So if t is large, then there's no bias. So this has nothing to do with our training strategy. This is infeasible Sharpe ratio. So you directly estimate it using sum of squared returns, right? So that's essentially how we do it. It has nothing to do with our strategy. Because our strategy gives you optimal feasible Sharpe ratio, right? This slide is optimal infeasible Sharpe ratio. Right. For to estimate that, we will have a bias. Okay. But this is actually well known and easy to address.
How does you have like a fixed number of factors? I wonder if people also uncertain about number of factors.
Right.
Would that affect the gap between the feasible and infeasible?
Absolutely. So as I said, so any additional statistical difficulty will enlarge the gap because rational expectation agents know everything in the DGP. But the arbitrage, the feasible arbitrage don't. Right. So that's why you make the problem statistically more challenging. having varying number of factors or weak factors, all kinds of things you can come up with. It will make statistical life suffer a lot, right? So that's why the gap will only become larger. So in fact, if you make alpha time varying and ask agents, suppose agent knows about it, you're gonna get a huge separation in practice. You can do simulation, you can see that very easily. Huge separations, okay? In practice, we never be able to know exactly the time varying alphas, right? How large they are. So you need to do estimations, smoothing that substantially drop the separation.
And very quickly, just contextual question. So you are saying with this statistical limits, uncertainty or parameter, whatever, it just makes it harder to reject potential mispricing, right? You are not saying
You put a lot more expressing. You put a lot more expressing.
right. Yeah. So it's just saying certain model is harder to be rejected, right? You're not saying like certain say the 27 factor you do they are wrong, right?
No, I think what we would like to target is an audience. At least we can target this audience, very precisely. Okay, so there's an audience like me who are interested in testing APT. Okay, testing these equilibrium models. All right, once we form a chi-square test, we got a statistics greater or chi-square test statistic greater than question. I reject APT. I walk away. All right, so this is the audience that I like to target because theory tells you that even though you see a significant pricing error, they do not translate into trading strategies. You cannot get such high Sharpe ratios. Right. So this is kind of the key thing we want to kind of address. Right. So it is possible that you have lots of pricing error, but there is no arbitrage opportunity at all. Right. So that's completely due to statistical limits. Right. So the literature used to feel like all based on random combinations. Right. So there's no statistics playing no role in here. But we can, this setting we find is interesting too.
So if you do that, if you build it in, how much harder is it to reject the APT on the data?
Yeah, exactly. Right. So,
Yeah. So what's the answer?
yes. So here we're thinking about economic rejection, statistical rejection.
Okay,
Right.
okay.
So we get a Sharpe ratio 0.5, and then you can use your economic prior to decide whether this is a realistically high or low. Right. So if you consider there's a trading cost, then the Sharpe ratio will be even lower. And that's the APT is not even right. Right, because right, so there's no that is feasible for you to trade.
Well, I think it's a follow-up question here, but due to time limitation, we can just take one more question. So anyone here? So because I saw quite a few hands before.
I think it's small.
So if you need to thank you, Professor Xiu, for very insightful and very